And we'll talk about some of the rougher edges on that. If you've used any other languages like JavaScript or Python, you have things that are, in Python they call them lambdas. In JavaScript we have the fat arrow functions. Those all create anonymous functions, closures. And today we're going to see how Rust does it. All right. So the first thing is that when we look at an anonymous function, it's not taken in isolation of the rest of the code that it's defined in. And what that means is that some languages don't have the idea or the ability to look at the context in which the function is defined in and take things from that context, but Rust does. And it's actually pretty common now. Most languages can do this. And what that means is if we come over here and we look at this implementation, OK, this is just showing us, I think, our old code. This is not yet the new implementation. Yeah, right here. Yeah, so here's an example. This here is what we call an anonymous function, a closure. And you can see here that the two pipes that are next to each other are delineating the argument list. So you can take different functions inside of this. You can take different arguments inside of this function, right? And this is just as if you declared it outside, like we have with fun. We say fn and we give it a function name. You could do the same thing, right? This is effectively the same thing. We're declaring a block of code. We're just doing it inline. And when we do it inline, it gives us the ability to reference stuff outside. We're going to see some examples of it. But the reason why we're doing it here is we're saying we're getting a user preference, right? And what is user preference? Well, user preference is an option, right, of shirt color. And what we're trying to handle here is the none case. So we want to effectively be able to say, if we don't have a shirt color, then do this thing, right? Now, where would you typically do that? You typically do that in anytime you have none represent there's been no value, and then you want to populate it with a default. That's a really good application of unwrap or else on an option. You'll use that all the time. So here we have user preference, which is an option, and we're saying in the event that we have none, then what I want to do is set it to default to this, self.moststocked, right? And it's going to effectively populate that shirt color with the most popular color. Now, what I was getting to is here, the self from self.moststocked isn't actually getting passed into the function. If it was, you'd see it right over here in between these pipes. So how does self.moststocked get into the function? This is the function. It's literally declared in between the parentheses, this one and this one. And inside of it, we have a self. How does it get into the function? It gets into the function through what we call closing over. So the function is declared in the context of giveaway, fn giveaway, right? So we have this function here called giveaway, and inside of it we have this expression which declares an anonymous function. And inside of that expression we say self. Self can see everything that's in that scope. So it can see self. This closure can see self. Self is closed over from that context. That's where the word closure comes from. So closure is typically, if you want to make the difference here, closure is an anonymous function that closes over its context. So originally these were two separate concepts, and you would differentiate between them. But now, because most functions that have anonymous functions also have closures, and they're the same thing, we don't differentiate. We just say closure. And we kind of mean the whole thing. But the point is that this anonymous function here, which takes no arguments, is closing over self. It's getting it from because it was called there, right? And that piece is where the name comes from. All right. So we're going to talk about some of the ramifications of that and how Rust does this safely, right? So the first thing we'll go over here is type inference. In the top, we have this thing called expensive closure. And expensive closure, well, let's say two things here about expensive closure. I just told you the historical definition of closure. It has to close over something to be a closure. Otherwise, it's an anonymous function. The book doesn't make that distinction. It's kind of gone in modern programming. But I just want to show you, this is an example of an anonymous function that doesn't close over anything. right? It's not looking anywhere except at its own arguments to make that definition. So that is the traditional distinction between an anonymous function and a closure. We would say expensive closure is an anonymous function. It is not a closure. But the distinction is lost, so if you see the terms being used differently, that's the reason why. It's not lost everywhere yet. It's still divisive. Here we have 4 different function declarations. They're declarations because the body of code is there, right? Of these 4 different function declarations, we have 3 of them, right, that have the prototype attached to them. And those are, well, the one at the top, right? Let's go through it. The first line shows a function definition, and the second line shows a fully annotated closure definition. So the first and the second line are showing you the types of the arguments. The top one is a function definition. It's not even a closure. If you look here closely, they balance them all out, but the one at the very top says fn. That's just showing you the whole function on one line. There's nothing special about that. All Rust functions have to tell you the input type and the output type. It's a requirement. They will not infer. They will use that information to infer other things like variable types, but the actual function itself must be strongly typed. And you especially have to know the output type, because then the whole language would fall apart. Add1 version 2 is not a function in the sense that it is not, it's assigned to a variable. So add1 version 2 is a variable that stores the function. The function it stores is anonymous. It doesn't have a name. I'm giving you all these different words because I want you to see how we kind of use them and think about them. The book doesn't use them all next to each other, but it helps if you hear them all next to each other. The one at the top is a function. The one at the bottom is a variable. Let thing is always just, you're declaring a variable. It's very useful. I haven't been driving for quite a while. You haven't moved, and now the signal's lost. It thought that was important to tell everyone. These 3 are variable declarations. Let is the variable declaration. And what are we assigning to these 3 variables? We are assigning to them closures, anonymous functions, using the term interchangeably now. So the one at the top, this one right here, version 2. Version 2 is typed to take a type of U32 and to return the type of U32. The other 2 are inferred. So whereas we could not infer it in a function definition, we can infer it in the variable, the variable typing. So when we have the variable and we're declaring an anonymous function, it can infer the types, the inputs and output types. Now, here's the thing about it. We went through this before, and I made a distinction, right? And I corrected someone else who's no longer with the class. Maybe it was the bad weather. That's what I'll blame it on. But I talked about the difference between inference and weak typing, right? I said, even though we infer, we are still a strongly typed language. Does anyone want to take a guess at what we meant at that at the time, or why that is important now? What is the difference?
Well, I guess because it is inferring in this case probably that is high everything, probably, which means if you were to later on have a second line where you try to now add 2.0, probably fail saying that it cannot add and then do it.
That is exactly right. That is exactly right. Even though the types are inferred, they are still strict in the sense that those types the compiler has made a decision about, so you didn't have to make the decision. But the compiler's decision can never change, just like your decision could never change. So whatever the compiler calculated the type should be when it infers, they must remain that way throughout the program's execution. It can't come back and later say, you wanted to give this a string, therefore I can infer it as a string. Game over. You're going to get an error. So the types are still strong. That function, by that name, still only ever has that input type and that output type. But it just decided for you what those types should be.
If you compile this, if I ever using the function, the bottom two. It wouldn't know what to infer. So, but it would be a no-op because it's never called, I guess. So it just skips it.
Well, you can still know because one is a literal or an I-32. And you can only add an I-32 to an I-32.
It could be a 64 or U. If you never use the function, the compiler wouldn't know what type it is.
If you never use the function, the compiler would know what type it is.
But it wouldn't matter because it's never used. So it wouldn't care.
I think it's just a decision they made. Like if you do x equals 1, it has to choose what does 1 mean.
No, it doesn't because it's strongly typed. It has to know.
Yeah, that's what I'm saying.
You're both saying the same thing.
Oh.
Yes, it has to know, and that's what he's saying.
But it doesn't know.
It does know. They decided that when it's a tempo literal, it must be an I-32.
No, it didn't because you never called it.
But what he's saying is still correct. If you put a 1 in a program, there's still a default type for that 1, right? Even if you never call it. So a literal 1 can be coerced or adapted based on context, right? Later on in the program, but it'll still have its type assumed, if not ever used.
What if you have binary x, y, and x plus y?
Let me give you an example of this. Let's come down here. Let's play with this, right? So here, let me show you how this works. Cargo new, bin foo, right? Now we're creating a binary called foo. Now I'm going to come down here and we're going to edit it. Now I'm going to come right here and we're going to say let x equals 1, right? You see where my editor is saying colon I32? The editor is saying colon I32 because that's the default. So if I do let x and well, someone tell me how to use this editor. Brian, you made me use this.
I didn't make you use it.
Yeah, you did. You said you should use lazy vim.
I told you should use Kickstarter. I didn't tell you lazy.
That's obnoxious.
It's weakly typed because it infers int 32.
That is a really weird behavior there, that it will not let you write that code.
I don't understand because mine was fine.
Now I double don't like you. That's going to make it very difficult. Yeah, let me see. Do I have another editor? Or I'll use VI. There we go. Okay. Gorgeous. Now, cargo run. Now let's come down here and we're going to go hello world. Cargo run. Now I get hello world 1, right? Now if I come down here and I say let y equals x, and then we'll do plus, and we'll do 8 U32. We can still run it. And now if I want to say, there is a method of getting the type out of it. Let's do this here. Let's just generate an error. Let z of string, of type string, equals y. Okay. Now you can see that y is a U32, right? Y is a U32 because I'm telling it to add x and 8 U32. Now let's see here what x is. I come up here and I say let z equals string x, like that. It'll generate us another error. And it'll say expected string found integer, right? That means at this point, it doesn't know what x is equal to. It still has it indecisive. And it's effectively saying that it is an integer. That's it. So it hasn't made the decision about what type to make x yet. But it will later on in that inference.
If nothing, it will just infer.
I32. Yeah, I think I32 is
If you have
it.
a function that's just x plus y, you would infer both of them to be I32, x and y.
What do you mean?
I see what you mean.
You don't give it a one.
Like basically making an anonymous function where you're passing x and y, and then you're returning x plus
Let
y.
fn equals, And then you're saying closing over x plus y?
No, like x comma y.
Right.
Those are the parameters.
Okay, I see what you're
So
saying.
returning x plus y.
Right, and you're returning x plus y. Let's give it a not keyword here. Right, like that. And now we're going to come down here and say fn, and then I'll give it oh, yeah, my fn. Expected string found U32. So the x plus y here is getting inferred as U32.
Is that because y is equal to x plus 8u32?
Well, let's see if I delete this. We can answer that question here. If I delete that, and I delete this, and then we come down here and I say, now let's see what it is. It's still U32. So it's inferring it as U32. But I bet if I come down here now and I put a negative in it, now it'll probably infer it as an I32. Right? Found I32 expected string.
If you don't put, if you just put x.
What?
Wait, go back. You say if you don't put in an argument, you just put x, y, right?
Right. That's no argument. Oh, here, I still have the x up at the top, but it doesn't make a difference.
So I'm guessing
There.
the trend seems to be they're trying to use the least useful type.
Just leave that alone.
Found I32, expected I32 found string.
If you never use the function, you never call it.
Then how are you going to know? You got to generate an error.
Okay, that's what I wanted to know. It generates the error if you never call it.
It'll generate a warning if you never call it. But I'm saying in order for me to know the type, I have to call it, right? So in order for me to get the error to tell me the type, I have to call it. Unless anyone happens to know another function in which Rust divulges the type without you calling it. I think the only way to get an error out of Rust is to call it and let it error. See what I'm saying? Like I'm creating the error here by us trying to assign the result of my function to string. How could I get the error out of it if I didn't call it?
So it just gives a warning if you don't call it. It just says unused function.
It just says unused function, yeah. Like this. That's just going to say unused function. Well, type annotations needed. Type must be known at this point.
So it is error.
Yeah. So if it has no information, it'll error at the very end.
It seems there's like a standard thing
That's why I
where
want
we can use type name. Put it type.
I think I did use that actually once. Is that a macro? How does that look? Is it like this?
So I found out StackOverflow once and they make a print type of function with type T.
Yeah, just send that in the channel. I'm not going to bother with that now. We're way off. Okay. So yes, anyway, there are complex inference rules that Rust uses, and it doesn't really matter because Rust can't make a mistake, right? Literally. If it infers the wrong thing, you'll simply get a compile time error, or everything will work. That's how it works. So you don't really have to worry about the inference rules in Rust. You don't have to wonder, well, what happens if it infers it wrongly? If it infers it wrongly, it'll tell you it can't do what it's doing. You got to go add the typing information. It'll be the very first thing you do. Oh, shit, why did it think it was this? Let me just go add that typing information back. It's not a big deal, right? So the inference either has to work or it has to error. It is a strongly typed language. So I would not worry about it all that much. These conversations about, well, what is Rust going to assume first? You know, like that last one, what is it going to assume in the event you provide no typing information and you never use the function? Well, first, if you never use the function, who cares? Second, you know, if you get an error, great. If it has default types, great. It doesn't make a difference because when you use it, Rust will validate its assumptions or it'll give you an error. So it can't be wrong under that axiom. This is not something I concern myself with. I've used Rust a lot and I've never wondered about that question because you'll get the error when it can't figure it out. You'll be notified. Let example closure. Okay, so this is what we call the identity closure, function. It's taking in an x and it's returning an x. So they're trying to show you here that the s variable has an anonymous function that takes a string and returns a string. And then n says to take that same anonymous function and to take a 5. And Rust is saying, I've already inferred the type for this. It's a string. This is the identity type for a string. I cannot return a different thing than the first one. I've made an inference. And this is what I'm saying. Anytime Rust makes the wrong inference, it'll just tell you, you know? What's up?
Is there a way to make that generic anonymous function?
Let's get to that later, you know? I think the last diatribe took us way out of where we want to be. And now it's 7:12 and we're still in the first section. Okay, so capturing references or moving ownership. We have here let list and we're giving it a new vector, and then I'm saying only borrows, and I'm saying this is effectively an anonymous function. It takes no arguments, and it is going to print from the closure the variable list. Now again, we take no arguments and we reference list. So we are, what is the verb? Closing over. Closing over list. We're closing over list. List is over here. We're taking the context that we were defined in. We're closing over list, and we say before calling closure list, only borrows after calling closure list. So in all of these, we are only borrowing list, right? And of course, they're all the same. And why are they all the same? They're all the same because the function only borrows doesn't do anything to list. It's literally just printing it out. So because it's just printing it out, it doesn't have to have a mutable copy, and it doesn't have to take ownership of it.
So you don't have to write the ampersand?
No. For the same reason, you would not have to write the ampersand if you were referencing list without the function. Imagine if you had this code right here, and you just got rid of everything to the left of that P. You would not need the ampersand, because you're simply referencing it. You're closing over it, and you follow through with that logic. Now, if you were passing list in, and you wanted the function to borrow the list, not simply borrow it by way of closing over it, but borrow it explicitly by way of its argument, then you would need the ampersand. You would have to have the ampersand in the variable declaration right here. You would say, you know, takes a reference to a vec named list, right there, in between these guys. Then you'd need it. Otherwise, you don't it. All right. Main. Main here, now we have this thing called borrows mutably. And borrows mutably is calling list.push. Now, list.push, Rust knows list.push requires a mutable copy of list, right? Has more information. So what is Rust going to do with that more information? It is going to change what it knows about that function. Why? Because if it is mutably borrowing list, then you can have, what are the Rust rules of ownership and references? What are they? How do they go?
You can have as many immutables or just one mutable, right?
That's exactly right. As many immutables or just one mutable? Yes, 1 point. You now have a total of 1 point.
Thank you.
You can have as many immutable references as you'd like to a piece of data, or one mutable kind. So because you can only have one mutable kind, Rust now has to know that that function is never called again, right? So it is going to tag that function as a function once. And we're going to see that in a little bit, right? That's how it keeps track of it. So it knows something special, requires a mutable borrow, and it tags it so it can maintain that tracking. All right, here's another thing here. Now we're calling this thing called thread spawn, right? Now, in case you don't know, Rust threading is beautiful. Because Rust has all of this information. Does anyone know what threading is? Has anyone worked with threads before?
Multiple things at once, right?
Yeah, but what does that mean? Threading multiple things at once sounds really good. What does it actually do? Whoa. Don't bail him out of this one. Yeah, threading multiple things at once is definitely what people say, but what does it actually do? Does it know?
The CPU is actually physically running two things simultaneously, or it could be using a physical mutant. Yeah, it's
The-
physically,
the C-
it's physically running.
There you go.
some
Just keep it. Yeah,
existing hardware.
yeah. Threading means that you have multiple different cores on your machine, and you can have multiple cores working simultaneously in parallel on the same task, right? That's what threading is actually doing. So if you have an 8-core machine and you want to make use of those 8 cores, you would write a threaded application to utilize those 8 cores. There are other ways in which you can balance workloads onto those cores, but threading is the most efficient because it has the least overhead for that operation, right? So that's really what's happening when we thread. Now, the question is, how does Rust do that, and what does it offer us in that? Because if you've ever just talked to other programmers, especially before Rust, it was described as very difficult, and for good reason, to do threading right. Why does Rust make it easy? Rust makes it easy because it knows which things can be called once, which things, and therefore cannot be threaded, which things can be called an infinite amount of time, and therefore can be seamlessly threaded without any work on your part, right? It has those distinctions built in because the whole language is built around with these traits and types that are about memory access, right? So here we're calling this thing called thread spawn, and thread spawn is going to take ownership of list, right? So now it owns list. Now, it is the owner of list is this new thread, and it can do whatever it wants with it. But nothing else can use list because you have moved ownership into that closure with thread spawn. So this new thread is this anonymous function right there. Takes no arguments. It moves what it needs into the thread, and now it has it in perpetuity. Oops, and I screwed that up. Yeah. Yeah, this is also kind of interesting. Let's cover this part right down here. If the main thread maintained ownership of list, right, and let's keep that code up there too. If the main thread still had ownership of list, so here's the other thing about threads, right? A thread can finish before your program. Your program can say, go do all this work, and everyone gets done with the work before your program is done. Or they can finish after your program. Your program can launch the threads, and then it can be done, right? So now you've got all these different CPUs working on a task, and it doesn't care to check up on them. Right? Both of these things are possible. If the main thread maintained ownership of list, but ended before the new thread did and dropped list, so the main thread is going to close now first. It owns list, if it owned list. It's speaking hypothetically here. It's not possible in Rust. But if the main thread owned list, and it just lets a new thread use list, what happens if the main thread dies first? It's going to clean up list. And the new thread's going to go, what in the fuck just happened? You gave me that thing, and now you destroyed it. You freed that memory back to the operating system. You're done with doing what you're doing, and I'm writing to it. Now you got a huge problem, right? That's one scenario that Rust is protecting you from. There's another one, though. The compiler requires list to be moved into the closure. Okay, I mean, it doesn't actually speak to the other one. The other one isn't really a problem here. The join keyword, by the way, tells the main thread not to finish before the thread you're spawning is done, right? Otherwise, the main thread can actually finish before, yeah. Anyway, we'll leave it at that. There are definitely a lot of difficulties with threading, and we can talk about how Rust saves your ass on a lot of them. But in the end, I think the bottom line is that try threads in Rust. It's a very simple process. You don't need to know why it's more difficult than every other language to appreciate the fact that it is really easy in this one. And that's really nice. I would say Rust's learning curve is very painful when you start. But by the time you're doing threading, you love it. Because if you've ever had to do something like that in another language, it's just massively easier. This is where it comes in, and you're more productive writing Rust code. Moving capture, and by the way, writing threading code is not something we typically do in Rust either, even though it's easier. And we don't do it in Rust because there's a lot of really good libraries that do it for us. I showed us earlier the par iterator. Does anyone remember me demonstrating that library? Yeah, it wasn't last class. It was probably a long time ago at this point. But I talked about, I like the fact that we have this iterable type and trait. And because we have this trait for iteration, we can adapt it and make it parallel under the hood. Right? Does anyone remember that part of the talk? If not, well then it's worth revisiting right now. Par iter is the name of it. So this thing called Rayon has traits for writing parallel programs using iterator style interfaces, right? And what is this doing here? We call input on par iter. This gives us the ability to iterate over the thing in parallel. And then we take a closure here called map, and this is squaring things. So it knows, because it's a parallel iterator, what can and can't happen to it. So map is not allowed, for example, to take ownership of something. Well, it's not allowed to take. Let's leave that out. Let's just say this: the function traits tell it what you can and can't do in parallel. And if you can't do something in parallel, Rust won't allow it. This trait is nice because you simply use it, and so long as that function can safely be done in parallel, Rust will do it for you. Otherwise, it will barf, right? Well, I mean, the way I/O works in Rust, you can do a lot of that in parallel too, because the unsafe part of I/O is in the file system, right? So the fact that you, yeah.
So the database is blocking.
Yeah. You can, what he's saying here is if you had I/O, when you're talking about writing to files and reading from files and directories, there's a lot of things that a file system has that are not atomic, right? So things that are not atomic, as far as the file system are concerned, are things like create this file if it doesn't exist.
So you can still use par to make a bunch of parallel Postgres queries, but the safety is handled by Postgres, not by par.
Yes, yes. And the same thing is true about file system calls, right? The file system just doesn't handle safety like that. It doesn't guarantee it. So you'll have effects that are bonkers, but it won't be Rust's fault. It's your file system's fault. The file system it doesn't have a command for create this file if it doesn't exist. So what you do is you create the file, and if it doesn't exist, it gets created, and if it does exist, it fails, and you handle the failure. That's how you write a safe file system call. And you do that because, at least on Linux anyway, all of the file systems don't allow that to be atomic. So the second, it's called the time of creation, time of use security vulnerability, like security. And the problem there is that when you check to see whether or not the file exists, the file could have had its state changed in between the time you try to create it. So those two different calls cannot be done atomically. So you check to see if the file exists, then you make assumptions based on it not existing. They may not be valid, right? You check to see if the file exists, it doesn't exist. What if someone creates it? You don't know. You check to see if the file exists and it doesn't exist. You got the, what if someone creates it? If it does exist, what if someone deletes it? Those two things can't be strung together. So the file system doesn't protect you against that, and Rust won't either, really. But that's a different type of, vulnerability. So here we have this impl for option, and what we're doing here is we're looking at this unwrap or else command, right? And unwrap or else is taking a function, and we already went through this. This is the ability to handle none and have it do something in that case. So unwrap or else here, we can see from the prototype, it's taking self, which is the option, and then this function. And the function must implement fn once, right? And fn once is something that all functions implement. That means that function can be called one time. All functions must implement that, right? Functions that can be called an infinite amount of time, they implement something called fn, right? And that means that function does not need to take ownership, and it does not need to write to it. So then Rust can say, and here, let me put it like this. Here's another way we could say this. If the function implements fn once, you can't send it to multiple threads ever. If the function implements fn, you could potentially send it to all of your different threads, right? Why? Because it doesn't necessarily have to write to anything or take ownership of it. So this would be something that you could purely scale outward, you know? And this is what you look for when you're using something like a GPU, and you want to make use of 6,000 cores. That's where you really get the gain. Because then you don't have to decide what core is busy, what can I send it to. You say, send it to all of them, let them all contribute to this workload, and take it back. Recall that T is a generic type representing the type of the value in the sum variant of the option. That type T is also the return type of the unwrap or else function. OK. Code that calls unwrap or else on an option string, for example, will get a string. Right. So unwrap or else, in the event that you are calling it on an option that was constructed with some value, does nothing. Because then there's no need to unwrap it, right? It's like saying, what does unwrap do on a result? Nothing, right? If you're on the OK side of the result, it will do nothing. If you're on the error side of the result, unwrap panics. So they're just showing you that it's the same. Yeah, let's go up there too to this. You see this F right up here where they're giving it that generic F? That is always how functions are typed, with that generic parameter, F. I don't actually know that that's true. I don't know that that's true. They all have their own unique type, but they also have type signatures, so you could do that still. Never mind on that. The reason sort by keys is defined to take a function mute. There you go. OK, so this one here we talked about before. We have fn once, which means it can be called once. We have a step up from that called fn mute, which means you need to have mutable access to it, that thing. And then we have function, which is the most restrictive. You can't mutate it. You can't take ownership of it. You can call it as many times as you want. So now we're seeing fn mute, right? Here we have this thing called sort by key. Sort by key takes the R, but it's calling sort operations.push. Sort operations.push means you have to have writable access to sort operations. Because you have to have writable access to sort operations, it's going to borrow a mutable reference to it. And as we've already established, you can only have one mutable reference, right? So this is fn mute. No, this is not fn mute. This is this. Oh, this doesn't compile. There we go. Attempting to use fn once with a sort by key. So here, let me explain to you this. Also, in case you don't know, the crab at the top right, I keep forgetting that, means the shit doesn't work. So if you're trying to make sense out of why this stuff doesn't work, it can throw you for a loop sometimes. Why this stuff works, it can throw you for a loop sometimes because it doesn't work. Sort by key is defined to take an fn mute. It has to have write access to the thing it's mutating. You cannot be more restrictive than that. You can't be an fn once. Here you're attempting to use an fn once with sort by key. And the reason why it's an fn once is because you are calling this sort operations.push. So you can only have one copy then. And that's where this error is coming in. Notice the other value here, r.width, right? This is reading it from R. So as it is sorting the list, you're only going to ever have one copy of that. So that is relaxed. It's not referencing one copy outside. As it iterates through that list, R is getting reset. All of those different closures can get a different R. And here's the error that it's giving you. So when you ran that error above, the code above, this is the error you got. And the error you got there is that the R was captured by the function mute closure, and the value here, sort operations.push, the value was taken. So the value comes from up here, and they're saying that you can only push the value once. And this makes sense. Right, so they're saying that this code up here didn't compile. Let's go through it. This code didn't compile, not really because of the sort operation .push. I was wrong. Compiler error wasn't that. The compiler error is saying it didn't compile because you're calling it with value. So what does that mean? It means that, let's say you have a vector and you want to push 20 copies of the same string onto it. You want that vector to have 20 copies of the string foobar. What do you have to do to 19 of those copies of foobar? You have to clone them, right? You have to clone them because the vector is going to need 20 different copies of the string foobar to have that vector exist, right? That's what .clone is for. I need another copy of it. The problem here is we're not cloning value, right? So we have one copy of it, and every time we sort by key, we're trying to push the same copy to this sort operations. We're trying to push that copy called closure called. And the vector is saying, I can't own 10 different copies by the same name. I must own the copy, I'm the vector. You have to give me a new copy to own. And it's saying, you've already given this copy to someone. So you've already given that away.
If you did a move into it, like if you moved the value into it so that it takes ownership, would it work or not?
No, and interestingly enough, for the same reason, because that's exactly what's happening. Right? What is happening is that value that you're referencing is getting moved. Move isn't always required. In this case, it's not required. The value you're referencing, value, is getting moved into that closure. It must be moved into that closure because in order to call .push on a vector, the vector must own it. So the vector is saying, I need to own this copy. You're giving it to me to push onto it. Therefore, I am moving this into the closure, and there is no longer a copy for the next function to call.
So does that push always move like a string that you put into it? Or?
Yes, and if you want to copy the same string into a vector multiple times, you must call .clone. Let me give you an example of this. Let's remove this from all this other stuff so we can see it. Let's say let my string equals string from, and then we'll say here hello world, right? Now I have my string, and then let's do this. Let my vec equals vec : new, and then we're going to go my vec dot push my string. This is the same problem. It's saying here that my string at the top, string from hello world, right, is getting moved with the first push. Subsequent pushes don't have it available. That's the problem with our closures. That's the very same problem they're triggering. They're triggering this problem here because we have, where the fuck did it go? Right here. Sort operations.push. Sort operations.push value is right here, and it gets moved in the first time, fine. It can't be moved in subsequent times. The error here is that you're attempting to use an fn once. Why is it an fn once? Because Rust knows that in order for you to push the value, it can only be called once. So Rust tags this closure, even though you're not doing it, it tags it and it says this is an fn once. But sort by key cannot take an fn once. Because sort by key is made so you can sort the different keys in something. In this case, it's in a list, right? So this list here is a vector of objects. We're trying to sort these objects. That's what sort by key is. So we create this list up here. It has 3 different rectangles in there. And now we want to sort them by something. So we call this sort by key, and it's supposed to sort all of these rectangles in this vector. So Rust knows I need to call this multiple times. That's in Rust's brain. And then Rust compiles this closure and it says, you're closing over value, you must own it. And I know you can only own one copy. So I know this closure must be a function that can only be called once, an fn once. So you're attempting to use an fn once closure in sort by key, which doesn't accept an fn once closure. What does sort by key require? Remember, we went through that list at the top. We said fn once is effectively the most restrictive. That function can only be called once. After that, fn mute. Fn mute can be called multiple times. After that, fn. Fn can be called infinite amount of times, right? So fn mute can have one copy of that writable reference at a time. Fn once can only ever be called once. You've taken ownership of something. And FN is great for multi-core applications, like on a GPU. You can send one copy to all 6,000 of your cores. So that's the thing there. But it's also kind of interesting because if you go back to my code and not their code here, right, it's interesting because this Rust new shouldn't compile right away. And the very same tools to stop this from compiling are almost just intuitive when you look at them in closures, even though it's a lot harder for you to figure out why the closure shouldn't work. Rust knows this language, and it's able to use this language here when it looks at this to make it work with a closure very easily. That same ability to identify these things, lifetimes, ownership, they work really well for deciding closures and parallelism and helping you out with concurrency. It is the same trick. Here you may look at it and go, I don't really need that, because you're used to Python or something where you can do this kind of shit. And then you have 3 different references to the same thing on a list or whatever. But Rust rejects it, and then it turns out to be massively useful with closures. In fact, it's so useful with closures that when I first saw this, I actually explained it to you wrong. Everyone remembers. So I thought it was because we were calling .push, which required immutable reference to sort operations. That wasn't the reason. The reason was because value was owned. And I totally missed it, but Rust caught it. And I'm telling you, this is the utility of it. You can do this stuff every day, and Rust still comes back to you and it says, that doesn't work. But I couldn't tell you why it didn't work without scrolling down and reading their error message. So my eye missed it, and Rust caught it. And that's good, right? I mean, nope, not. Kudos to Rust. I made one mistake. It ain't a big deal. I'll fucking brush it off. But I'm just saying that's nifty, right? All right.
You're chugging those Diet Cokes.
My second one.
Still.
All right, mother dearest. How much is it going to pain you when I sip on this?
Not that much. I'm just saying. That's just an observation. That's a statement. All right.
It's a good statement.
Yeah. I mean, there's nothing about the statement. It's kind of one way or the other.
Yeah. All right. This kid's going to come over to my house. I'm going to put him to work for a day. And then he can lecture me about health. All right. So we have the last one here, using an FN mute with an FN mute closure. OK, so here. I want to go back to it and say why I thought that was wrong and I made all those mistakes. We're going to go back up, and we'll talk about that for 1 second. Sort operation does have something special about it. It is not as restrictive as I was pretending it to be, but there is something special about it. Sort operations.push means you have to have a mutable copy of sort operations, which you're not passing in. So it has to close over that. It has to have a mutable reference to it. You cannot run multiple copies at the same time, because it is potentially even destructive. And why is it destructive? Does that make sense to you? When I say you can't run vector.push at the same time, why?
Because if you already push one thing, you're pushing another that can conflict. So,
Well,
I
it's
mean,
not, right? 'Cause you get-
Yeah,
once you
it's
get
already
pushed in,
moved.
yeah.
No, it's the value that you're pushing.
Yeah, that's right, Kai. So that's not the right reason here. Let me explain this to you, right? The value is the reason why this didn't work. But now I'm asking you a different question. I'm telling you, let's say that the value is created anew inside of that closure. Why then would sort operations.push be FN mute and not FN? Why is that distinction needed? Why can't multiple things push onto a vector at the same time? Obviously, they can't push the same value onto the vector at the same time. Why can't they push different values onto the vector at the same time?
It's a sequence.
No.
would it go over vector capacity or no?
I have a feeling you're going to get this right. Let's see.
Right, so a vector is an array that we store in a heap, right?
Mm-hmm.
So, well, I guess kind of it.
No, you're keep on.
So like, if you try to push multiple at the same time, you don't know if you're gonna run beyond the current size of the array.
That's right. That's exactly right. Good job. Good job. That's exactly right. So let's talk about that for a second. Different structures have different ways of laying out their memory, and they handle push differently. What does that mean? It means that Does anyone here know what a linked list data structure is? We have 2 people who know what a linked list data structure is. OK. In a linked list, you can keep adding new things, right? Because the next one doesn't have to be connected to the one before it. You can go say, give me this. I still need the same amount of memory. Not changing the amount of memory it requires. But I have to store one extra pointer to it. And now I can just keep doing it. You get this fragmented data type. But it can be all over the place. And what does that mean? It means that you never hit a point in a linked list where adding another element to that list will require you to move everything. But it's not true with a vector. A vector has a capacity. You can call vector : new with capacity and tell it how many elements you want to store in that vector, right? What is the problem with a vector? When you run out of space in the vector, what happens under the hood is Rust says, I need to go allocate more space for the vector. It moves your old vector into the new space, right? It makes sure that all of the old vector references are invalidated. And then the new space for the vector is where the vector can grow. That's what happens when you exceed the vector's capacity.
So just to make sure I understand this right, on the stack, that's whenever the program knows this is how much space I need, this is how much I get to use. But on the heap, it's like, I think I need this much, but you can run over.
On the heap, you cannot run over on either of these, right? On the stack, you can allocate more memory and grow your stack frame up to a certain point. There's an underlying C function called realloc, and it just says I need more space on the stack. And if it just happens to be that your vector is the last thing on the stack, you can get more space on the stack and just give it to your vector. That's how you do it in C. I don't know that any of this stuff is how Rust does it. I'm just telling you why this isn't possible. But on the heap, someone else could have requested memory right after your request, and now you're blocked in. You came after the guy before you, and you're coming before the guy after you. So you may have just the block, and now the question is you've ran out of capacity. And the thing about a vector is you always have to have constant access time. So you got to be able to say, I need to access the 5th element, and you got to, that's where the 5th element is, you know? That's what you want. So you look at the vector, and a linked list, you can't do that. Let's be clear about that. I talked about a linked list doesn't have this problem. That's because to find the 5th element on the linked list, you have to find the first one. Then the first one tells you where the second one is. And the second one tells you where the third one is. The third one the fourth one the fifth. So it's called ON access time. The longer your linked list is, the longer it's going to take you to find that next element when you start from the start. But when you're talking about a vector, it has a different performance profile. It has to be able to seek. You can seek to the 5th element, the 6th element. Get is always very fast. Doesn't mean if you have 10 elements or 10 million, right? So when you get to the point where you can't store another element in a vector, what Rust does is it takes the entire vector, allocates more space for it, and moves it in memory. And that can cause a slowdown, right? So you don't want that to happen. You want to declare vec with capacity, if you know that information beforehand, the reasonable capacity of your vector. Then you can stop that from happening. That's why these functions exist. Remember, Rust makes assumptions, but it will always give you the ability to do the rightmost, I would say, the rightmost thing. So it's right down here, new with capacity. std vec new. Oh, here, look, push within capacity. I didn't even know this exists. Appends an element if there is sufficient space capacity. So this will stop that from, it'll stop it from happening, the ability for it to resize it. Otherwise, I bet here, if the vector's list would exceed its capacity after the push, O capacity time is taken to copy the vector's elements to a larger allocation. It's telling you right here. It's telling you that under the hood, a vector, when you try to push with it, if you exceed the capacity, then it's got to copy everything. Copy all of the vector's elements to a larger allocation. It's going to do that all underneath the hood for you. You don't see this stuff. It just happens. And if it gets in your way, you're profiling, you're saying, why is my vector getting slow when I'm adding 10 million elements one at a time? There is methods to stop it. Like you can say, you know what's scaring me about this is, There, vec with capacity. So I wanted to call it new with capacity. It's vec with capacity. You say vec with capacity, and you can tell it how many elements you need. It'll pre-allocate that space, and then hopefully you won't exhaust it. It won't have to do these constant, I need more space, and I'm going to remove my vector. But the point that I'm trying to make here is, well, first, I want to say that rant I don't regret having. It's different. You need to know this stuff. I want to say sort operations dot push, even if the value was declared inside of that closure, even if that was the case, this would not be valuable, would not be valid. And it would not be valid because if you were to run multiple copies of this at the same time, one of those copies could have exceeded the capacity, and Rust may have already moved the entire vector somewhere else in memory. The other copy, still running at the same time, will have a reference to the old copy. Rust won't have an ability to say, update this reference in all the threads. Only the thread in which moves the vector can have that reference. So how are you going to update all the other threads? You're not. So the point that I'm trying to make here is that distinction is what I'm trying to get at. The distinction is, this doesn't work because we can't push multiple copies of value when the first copy needs to take ownership of it. That vector needs to own value. We can't give the vector ownership of that value multiple times. First time you give it to it, the vector owns it. You no longer have it to give. That's why this doesn't work. If the value was declared inside here, it still wouldn't work because that would be an FN mute, right? So it would say effectively, I need to make sure, rather, that I'm not calling this multiple times at the same time. Let me back up for 1 second. That would work because sort by key requires an FN mute. But my question originally, how I got on this diatribe, was I said, what is the problem with pushing onto a vector from every different thread at the same time? That's how we got here, right? And I was trying to show you that there's no world in which that's OK because vectors under the hood may change their location in memory. And you wouldn't have a way to communicate to all the different threads that, right? So this one here, it's saying attempting to use an FN once closure with sort by key. Sort by key is an FN mute. So this would be fine. You can still mutate things. Down here is an example of that, right? We have list sort by key, and then we say num sort expressions plus equals to 1. And this one doesn't have the annoying crab at the top right, which means the code works. I think a better interface would be to color them red, you know, or like shade them with red lines or something. Maybe a little bit more in your face. But anyway, this one works, and it works because the value is created inside the function. It's just 1. It's a literal, so it gets created inside of the closure. And num sort operations right here, this is mutated every time the closure is called. That's totally fine, right? Because sort by key can do that, right? Now, what does that also mean? That means because this is an FN mute, you can't run it in parallel over multiple threads. You can only run FN like that, right? So you can run one copy at a time. OK, processing a series of items with iterators. So now, it's interesting enough, we're going back to iterators. We already started this off. I said iterators were a really useful pattern. I went and I talked about how they kind of unify the language Python. And if you remember that class, I said I like Rust because it has those same patterns, those same unifying abilities, that same coherence in the libraries and in the language, and it has more of that. Even though it is considered to be a lower level language, it has higher level abstractions. It has iterators, it has a lot of other things that we'll see here. Now we're getting back to iterators, and they're showing us these iterators. And here's how that works. We have a vector we call v1.iter. Now we have an iterator, and we can suddenly loop over it. We can say for value in v1.iter, do this thing, and it'll do it. It's interesting because the for value in v1.iter, this thing here, v1.iter, need only implement into iterator. So if you give it a function that implements into iterator, or a struct that implements into iterator, or a vector that implements into iterator, anything that implements that trait will be able to be called in that context. Rust will transparently do it for you. But here they're doing it manually. They're taking v1, which is a vec, and they're saying convert it to an iterator of those elements, and then let me use that in a for loop. And here's the iterator trait. And I told you that this is why it's kind of cool. You can implement this iterator trait on everything. And when we talked about this last time, even though I didn't show it, we talked about one of the areas in which you may implement this is when you're iterating over rows in a database. You say, go select all of the vehicles in the vehicle table, and then it's going to return you a result set. When you iterate over that result set, give me one row from that database, right? And you can process it. So this is an example of you having a result set object, being able to iterate on top of it. It breaks down really well. It makes things very easy. It's one of the reasons, in my opinion, why Python is so easy. Python really only has this tool. They've added a couple more recently, but it really only had that tool for a very long time. And that tool was so powerful that if it was the only tool you grabbed, it kind of unified the whole language. Everything kind of breaks down into an iterator in Python. So you want to read from a file, what does a file return? Lines. You want to read from a database, what does it return? Rows. And you iterate over these things, and it's the same construct everywhere. OK, so Rust has this too, and we can do the same trick. Here they have this vector 1, 2, 3, 4, and we call v1.iter, and we get this iterator. And now what we're doing is we're iterating over it, and what they're showing you is every call to .next is going to give us the next element from that iterator. And this is what for is doing under the hood. This is actually how it works under the hood. For is actually calling .next, assigning it to the value, and then invoking the block with it. Methods that consume the iterator. So here we have this thing called sum, right? And think about what sum has to do. It has to iterate over every element in that iterator and return to you the aggregated value, right? A representation of that iterator. In order to do that, it can't maintain the state of where it was at before. Right, it could, it doesn't. So what it does is it iterates through the entire iterator. You don't have any idea of where it was at, where you came from, how many elements are left, any of that kind of stuff. And then the iterator no longer exists. You can get another iterator. It wasn't the last one, but the iterator no longer exists. It has been consumed by sum. Sum has used that iterator to store its state as it went through the list. Now, what you should ask, which is kind of amusing, is what happens if you call next before you call .sum? Well, then you just skip that element, right? So if you actually use .next to put yourself, that iterator, in a specific state, and it's not the very first element, well then .sum will say, I didn't see that element. You iterated through it before you gave it to me. I will consume the iterator now, but I missed that element. And that's actually how take works and some of the other things. They actually do that under the hood. They just skip one and return it to you. Move the iterator to the next step and return it to you. OK. Methods that produce other iterators. So map here is taking an iterator and returning another iterator. This is what allows you to chain these things. I talked about that first. Remember that conversation I said it was really useful for me learning Rust? I was in the channel, and there was another guy on there. His name is B3NNY. He's a Microsoft employee. And I was being a super pain in the ass. He's a super cool guy. He was teaching me how to write very complex Rust because I kept asking the question, how do I do this all in one line? And it was an HTML parser, and I wanted to do the whole parsing statement in one line. So I wanted the whole line to be things that returned iterators so I could call them again, and we could keep chaining things down. And it made this very complex code, but I learned a lot in the process. This is the trick that you have to use, right? If you want to continue iteration, you can take the iterator and then simply return the next element in it. Is another iterator. So you're making your map return another iterator. OK, so yeah, this is the point here that they're trying to make. Iterators are lazy, and they do nothing unless consumed. This is a little bit of work to wrap your head around, right? Sum consumes the iterator because it visits every element that's there. It says, in order for me to sum, I have to read the entire iterator. So sum exhausts the iterator, going through every element, seeing it, and adding it to a total, right? But an iterator by itself does nothing. It needs to be consumed. So if you just have map, which takes an iterator and returns an iterator, and nothing needs an element from that, then map will do nothing. Map will take one element from the iterator, return an iterator. When you say you need an element, map will say, here's the element. Now, map doesn't have the element, so it goes and gets the element, and it applies the function to it. That's how it works. So map kind of creates a pipeline. It can create a pipeline between iterators and iterators. And the thing about it is, if you don't pull, something doesn't pull an element from that map, map will not pull an element upstream. So they're showing you here that v1.iter.map x1, x plus 1, will do nothing unless you actually need those elements. You have to consume them all. Now, if that doesn't make sense to you, this idea that you have to consume them doesn't make sense to you, and that's fine. It's very easy to make it make sense to you. And I'm going to show you how. I want to look at this here. Let's take a look at this. Let's go back and let's do the same thing that they did. v1 equals vec, and then we'll say here 1, 2, 5, whatever, like that. Good. OK, this doesn't work. And you may say, well, why doesn't it work? It's very clear what I want that to do, right? It doesn't work because something needs to consume it. And how do you consume it? Well, one way to consume it is with collect. So we can come down here and say v2 equals this, and then I can say dot collect. Now it would work. Why? Because now I am collecting all of the elements into it, and I'm assigning them to v2. So v2 will be a vector. If I do this, now I have a map. v3 isn't a vector. v3 is a map, right? So the map says, I'm ready to produce to you values. I am an iterator. I'm ready to produce values for you. You must pull them from me. And if you never pull those values, it doesn't do anything. And if that doesn't make sense to you, right, remember that under the hood, for works by calling next. So for says, I'm going to iterate through every element, and I'm going to call next on it with this body of code. For is pulling the values. It is calling next for you. In this context, someone has to call next. If you call next, that's fine. Collect will call next under the hood, that's fine. But if no one is calling next, no one is pulling values, the map will do nothing. The iterator will do nothing. An iterator that is never called does nothing. Something needs to call it, and they need to say next, 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 or whatever you want. The first next even, totally fine. You have to get those values with next, or the iterator will do nothing. Collect is the canonical way to make sense out of it. So when you look at this and you nod your head and you go, I don't really get it, just keep in mind the collect version isn't much more, and it does exactly what you want. And you just have to get used to seeing it without collecting, going, well, what would that do? And get used to it simply saying Rust doesn't accept that syntax. There is no implicit collecting. You want an implicit collecting, but it's not an implicit collecting. Map is returning an iterator. That iterator will process code, pulling values as you need them. It is lazy by default. Yeah?
So that error, it wasn't an error, it was a warning that it threw on the Rust book that said you're not calling it, so it's not really doing anything.
Yeah.
It was a warning, not a failure.
Yes. Yes, it's a warning. And it's a warning because the code does nothing, but it is not unsafe. And someone else made that clarification. I also made that mistake, because I would never have that in my code. I would just delete it. And the same thing is true about using a result and not checking the values. I just don't write code like that. Never intentionally, anyway. I may disable that while I'm writing a test for the class or something like that. But it's so easy to just solve those. You're talking about one line. And when you're good at Rust, it's one line in 1 second. you know? So it is fucking nothing. And this editor that fucking Brian's got me set up with, I can't even stop it from typing out my shit, you know? It just does it for you, you know? So yeah, I'm saying that it is a warning. It's very easy to fix, but yeah. Otherwise, it's just a piece of code you're never calling, you know? Like any other piece of code you don't call.
Yeah. Can you go back to the code?
Yeah.
So does V1 exist after the second line?
No.
Right.
No. So V3, it will not run with V2. I was just talking through these, yeah. If you want V3 to run, you would have to delete V2.
Yeah.
Okay? Yeah. This is more just so I could show you what this looks like. Because I'm not used to this syntax either. Like you nodding your head, this is the first language I've ever used that did this. For every other language, iterators were not lazy by default. So you didn't have to do that. You hadn't, if you called .map on a collection, it would return a collection. You have to get used to an iterator in Rust not returning the collection. It returns the iterator, right? Then collect says, I want to return the collection. I need to consume all the elements and return the thing, the vector, the hash, whatever. And this is, in my opinion, far better. So even though I had never worked with a language that had this primitive in there like this, it turned out to be far better.
So what V2 holds now is a vector after?
Yeah. V2 holds the vector and V3 holds a map, which is an iterator. And you can see that here. If we do something like rs std map, std iter map, an iterator that maps the values of iter with f. This struct is created by the map method on an iterator. So the struct map is an iterator, right? That means it doesn't implement into iterator. It is an iterator. It implements iterator. If you go down here to source on it, and you look at this map struct, you should see. Don't make a liar out of me. I'm just going to stop reading core Rust when I'm in a class. I just make fucking assumptions about it, and they're all wrong all the time. No, here it is right here. IMPL BI iterator F iterator for map I. Okay, that is a really ugly type signature. But what I'm saying is, it is effectively telling you there is an implementation of iterator on map. So I told you everything can become an iterator by implementing into iterator. That allows the collection to act like an iterator in some contexts. You can also implement iterator itself if you're creating your own iterator, and that's what map did. You know? And this sounds complex, but I'm saying that when you see map as a type and it says capital M-A-P, map, that is actually also an iterator. So don't let that confuse you. There are, when something takes an iterator and returns an iterator, I like to use that words because it communicates to people what's actually happening. The typing of that is not that. I am lying to you intentionally. Map takes something that is an iterable and it returns a map which is an iterator. That is complex wording. It means the very same thing, right? And that is literally showing us there, right? So let's look at that type. Let's just look at that and try to grok it, right? It sounds scary, it looks scary, but it's really not that scary. The B is the thing that the function mute is returning. So B is the type of when you take an item, you're iterating over the item, B is the result of that iteration. Let me give you a case in point. Let's say that I take a string and it's first, second, third, fourth, fifth, and I return the number 1, 2, 3, 4, 5. The item is going to be self-item, item. That is the type I'm taking, the string, first, second, third, fourth, fifth. The B is 1, 2, 3, 4, 5, right? So you're iterating over it, you're taking the string, you're returning the number. That's what the B is. The B is saying that's the result of the function. The I is the iterator. I have a list that says first, second, third, fourth, fifth is strings in that vector. The I is saying that that thing I am iterating on, it must be an iterator. I need the I to be the iterator. So I can do that. I can see things like that. I can call next on it. Okay? Now, What is interesting here is the iterator is not a type, right? It is a trait. That's why I said, when I said I take an iterator and I give you back an iterator, and I said that with map, I was being lazy. It's not just that I was wrong, it's that that's impossible. Because iterator in Rust isn't a type, it is a trait. That's what they're showing you here. The I is the type, and it can be any type that implements iterator. So when I say an iterator, that is, in some sense, not true. The right phrasing of that is any type that implements iterator. I'm just being lazy. An iterator, colloquially, is any type that implements an iterator. So the type that implements the iterator is I, right? Then I'm implementing the trait iterator. Again, that same thing. I'm implementing the same thing I'm taking, which is an iterator. I'm implementing that trait iterator for the map. So now I'm telling it, this type I have called a map, I'm telling Rust how to make that map act exactly like an iterator. So I said iterators don't exist as a type. An iterator, as we say colloquially, is any type that implements an iterator. And I'm writing the implementation right here on line 100. So map is a type that implements iterator. That is what it looks like to implement iterator on a map. This is a deep dive, but I'm trying to show you a little bit how it kind of fucking works. Because there's a lot of times where I say things because I'm lazy and because I don't want to go into the deep shit. But I feel like if I'm already in the core and I'm trying to make a point, we're already in the fucking weeds. As might as well try to explain it and people can ask questions. Does that kind of make sense? Help out a little bit? Cool. Map is a type. Map has a struct definition right there, struct of map. It has, it takes, the type of map is such that internally it must be an iterator and it must have a function. And that function tells you how to iterate over that. So it is a struct. A map is stored in a struct, and that struct implements iterator.
So you're calling that map, you're actually constructing.
When you call .map, you are telling Rust on that iterator, I wish to return a map. The map is going to iterate over that iterator, and it's going to apply a function to it.
It's constructing a map. It returns a new object.
Right, exactly. It returns a new object, which is implements iterator. Yes. Okay. All right. It's very easy to get tongue twisted on this stuff.
Or it's a factory function.
Okay, so we have vector v1 is a vector of i32s, and we have 3 different values in for it. And now I'm saying v1.iter.map.collect. This gets down to what we want. When we say, what does it mean, you're returning another iterator, that's not doing anything until you call it. Collect is actually calling it. It's exhausting it for every element that remains in that iterator. And now what do we have? We have v2. What is v2? v2 is a vector. We don't have to say what items v2 is iterating on. We can let Rust infer that. Why? Because we know what types the map must return, because we know you are iterating over v1. So Rust is smart enough to know that a map over v1 will return the same types as, well, whatever that type is, the return type of that function. That was the B that we just talked about, you know. So it will infer that. Using closures that capture their environment. OK, now we're back into closures. So here we have shoes.intoIter. And remember, shoes is this struct up here. Shoes is a vector of that struct. I'm sorry. Shoes is a vector of that struct. So we have a struct called shoe. We have a vector of them, which we call shoes. And now we say shoes.intoIter. This is going to return, it's going to return an iterator on that vector that returns every element in it, which is the shoe. And I'm going to filter that. What does filter do? Does anyone know what filter does?
It returns an iterator with things filtered out.
Returns an iterator with things filtered out, yes. It's lazy though too, remember? So what filter does is it gives you a function, right, in the pipeline that will effectively say this. When someone wants to pull a value from the filter, I will return the value exactly as is if my function evaluates the true. If my function evaluates the false, I will simply look at the next element in the iterator, pull that, and evaluate it. If it returns true, I will return it. Otherwise, I'll keep going. Filter is also lazy. It doesn't have to read the entire vector, the entire iterator. Filter only ever needs to look at one element at a time. And if that element passes the filter does nothing. It's a no-op. If the element fails the filter simply says, I need to pull the next one. Don't give that one away. Throw that one away. I'm done with it. Give me the next one. That's kind of how filter works. So here we have a filter, and we're looking at the shoe size and seeing whether or not it is equal to the shoe size we pass in. So we have a function called shoes in size, and that's taking a shoe size, and we're iterating over a vector of shoes to say, does the size match that one I'm looking for? If it does, I'm going to return it. Now, I will say this. One more thing I will say. No, I'll say a lot more. That's what I do. The dot collect here in shoes and size is not ideal, right? It's a sign of being a novice, right? I told you that you can add dot collect and the code will behave as you want. That's what I said. It doesn't mean that that's what you want it to do. That means you're probably comfortable with that. It makes sense to you. Because now you're thinking, I have this collection of things. I have this list. I have this hash, whatever. It makes sense to you. You feel good about it, right? It is easier to comprehend a concrete grouping of things than it is to comprehend a pipeline. But if you keep it in a pipeline, your code will be much faster. It'll always be more efficient because you don't pay a cost for the laziness, right? So if you don't say collect here, and you don't return a vector of shoes, and instead you return something that is an iterator returning an item of shoe, right? You return an iterable struct, like a map or something of that sort, right? If you do that instead, then the person that calls your function may not need all of the shoes. Let me give you a case in point. Let's say you have a small shoe shop and you're doing this on Amazon. Amazon has 50 million shoes. You can only use the 50 best-selling shoes. That's it. You have a small boutique. It's a retail store that hasn't grown under capitalism to devour all of its competitions. They're still friendly. They smile at you. That's a boutique. Amazon is not a boutique. So you have this small shop, and you only want 50 shoes. If you have to call this function on a data set like Amazon, you're going to get a fucking lot of shoes you don't want. And there's no way to stop it because you've collected it. If you return an iterator, then the person that needs that information can decide, take 50. That's it. I just need 50 of them. Yeah?
So if you're like the large collection of or list that you're working with is small, dot collect would be okay, but if it was like huge, then that's where you pay the price of doing dot collect.
Okay, yes, for some degree of yes. And what I mean by that is, it is okay in the sense that it sucks less when it is a small collection than when it is an Amazon-sized collection. But there's still no benefit of that, right? Collecting, except by the last person, is kind of an anti-pattern. Keep things as a pipeline and let people play with that pipeline. Give them that pipeline. Then they can do whatever they want. They may need one item. They may need 10 items. You're right. If you give them 10 items and they only need one item, you've only wasted 90% of your processing power. That is probably not that bad with a 10-item list. If you give them 100 million items and they need one item, they're probably going to be a little bit more upset, you know? But still, is giving them 10 items when they only need one a good idea? Not really. No, there's no point in it, right? So I would say it is an anti-pattern. It doesn't. There's no need for that, you know? Now, if you're working with ownership, you're going to eventually have to turn that into a vector, something you can own. Because you can't own the elements underneath the iterator. You have to collect them into something you can own. So sometimes you have to do stuff like that. right? And then there are other times where you cannot keep things in a pipeline. And I just say pipeline. What I mean by pipeline is a chain of iterators. You can't keep things in a chain of iterators. When would this be the case? This would be the case for something like, let's say that you are building a sort mechanism, right? With a sort mechanism, you can determine the highest element by visiting all of the elements and just storing one value, the lowest element by visiting all the elements and turning one value. But if you need to determine the, if you need to sort the list and find the odd numbers or something of that sort, or sort the list and find the bottom 20%, you know, now you're going to have to visit all of them, and you're going to have a buffer place to store what is the lowest 20%, not just the lowest one. So in these types of situations, you're going to have to visit everything in there anyway. You're not going to be able to keep it in a pipeline. You're going to have to visit everything. You know, I guess even in the top one and the bottom one, you have to visit everything. You know, in those types of situations, you can consume the pipeline and just return that one thing. But you know, for most of the stuff that they're giving as an example, we don't have to do that. The shoes and size function takes ownership of a vector of shoes and a shoe size as parameters. It returns a vector containing only those shoes of a specified. Okay, duh, we just did that. Removing a clone using an iterator. Okay. So we have these two things here, args1 and args2, and we're cloning them. But we didn't have to clone them. We could have used an iterator on it. So here's another way to do that. We could do config build args unwrap or else, and then say that there's a parsing problem. But look above it. We do this thing where we say args, and we say env args collect. So yeah. Okay, what's going on here is args1.clone is required because we can't remove that item from args. We can't take args and steal the first element from it. It has to own it, right? Now, if we come down here and we look what's happening, we see env args collect, right? Now we're visiting all those different elements and we're collecting them all into one vector of strings, right? I don't think it makes a difference under the hood. So I don't think they're actually optimizing anything out. I think that env args collect is effectively going to do what the other one was doing. It's just going to be smaller, you know. Rather than having to say .clone every time, you simply don't have to say it.
Cloning returns a newly allocated string.
Yeah, but so does .collect.
I'm not arguing. I'm just.
Yeah. I think .collect does too. I could be wrong, but I do think I think .collect does that.
What was the one that doesn't copy the string? It just returns a new container.
Doesn't copy the string?
The slice. That's it.
Yeah. The env args function returns an iterator. Rather than collecting the iterator values into a vector and then passing a slice into config build, we're now passing ownership of the iterator. Okay. Yes. So what they're showing you here, okay, now I get it. Now it makes sense. Here they do the .clone stuff, which they have to do because they can't take away from env args those elements. They can't own them, right? Because the argument list must be owned by the program. You can't destroy that and then say, ha, I fucked up your argument list, now deal with it. It's actually, I believe the environmental arguments for the program are stored in a different part of memory. They're stored in static memory, I think. So I don't even think that that's possible. But here what they're doing is they're showing you can do envargs.collect. And when you do that, you have now a new vector, which has the same things that the envargs had in it. And I simply said, I don't think that there's a performance benefit to that. So this is just style, which is uninteresting to me. Now they've come out with an idea in which there is a performance benefit. Now they have this idea here where they are going to pass env args without calling collect on it to config.build. So if you remember the last class we did, we made something called config.build, which took the arguments. But it didn't have to take the arguments. It doesn't have to own the arguments. It could take the iterator to the environmental arguments. Now it can iterate over them, and it doesn't ever have to own them. So there's an iterator to the environmental arguments. You can create that iterator as many times as you want. It's a read-only iterator. You can give that iterator to config.build. It can read the arguments without ever making a clone or a copy of them. It doesn't have to collect them into a new data structure. It doesn't have to clone them to a new location. So now they're saying, this is even shorter and it's more powerful, and that's true. All that they have to do is give the env-args iterator to config build, and they have to adapt config build to take the iterator. So now they're showing you what it looks like to make that adaptation. We have this mute args in here. So now the config function we had before has the config struct we had before. We had a struct called config, and it had all these different values on it. It has a function called build, right? And build takes a mutable argument right there, which is something that implements iterator returning a string. So this is the definition, IMPL iterator, item string. It is the definition for something which implements the iterator trait returning a string when I call next. Remember, the iterator, when you call next, returns the element. So you have to have a way to type what the element is. This is why you can't have a vector that has strings and numbers in it. It would fall apart. The iterator has to know what it's iterating on. So it's saying here that the iterator must be typed such that the item it's returning is a string. This will not accept an iterator to numbers. And that's the syntax for that. You say iterator, and then you give it the generic syntax, and you say item, which is what that's defined as. It's called an associated type. Inside must be a string. Using iterator trait methods instead of indexing. OK, so now we're passing this iterator into build. What does it look like to use it? Well, this is what it looks like to use it. Now we determine the query not just by looking at the arguments, because the argument just says here's an iterator. We determine what is a query by calling args.next. And then right afterward, now the iterator has a different state inside. Something else has consumed the first element. We've changed where we're at in the iterator. Now file path is going to call args.next. It's going to get the next element after it. So now we have this location-sensitive iteration. The first thing that calls args.next gets the first element. The second thing that calls args.next gets the second element. And none of them are copying them. They're all by reference. And then we have let ignore case, and we're saying that equals envar ignore case, right? So now we are putting ignore case to that environmental variable. And then we are returning this new config type. So now we have a builder that is taking an iterator instead of the positional arguments. Making code cleaner with iterator adapters. OK, so this is what our code looked like before. And we were doing all of this type of stuff. And this is what I refused to do when I was learning iterators. So now you're going to see the wank off task of just using what they're calling iterator adapters here. Now, these get called a lot of different things. Iterator adapters is the simplest word for this. I think the other words are, what is the other word for it? Combinatrix or something like that? I forget. But anyway, iterator adapters is this concept of this pipeline that we're building. We're building a pipeline. Everything is an iterator returning an iterator. So now we have this thing here. We're saying for line and contents.line, line.contains query, line.push line. Right? We could just as easily say let mute results equal contents.lines. Now we have contents is an iterator. .lines is going to split that thing up by lines, new line. Dot contains is going to be effectively filter. So dot filter where query line dot matches query. That would be your filter statement right there. And then results dot push is effectively going to be dot collect. If it meets it, collect it. And let's see what they wrote. There you go. So it's the same thing. So this is the short way of doing it. And you can play a lot of games. You can learn a lot by simply saying, I want to learn that way. I want everything to be one chain of iterator adapters, and waste tons of time. You know, but it's a good learning experience. So lines, filter, collect. And the only thing I got wrong is I said I would use lines.matches, and they just used lines.contains, which was what the other one said too. So cool. Choosing between loops or iterators. Yes, it's all style. It all gets compiled the same. Loops are looked down upon because they're for the weak. No, I'm kidding. Loops are very common. They're totally good. There's nothing wrong with them. However, they certainly are less fun. That's what you should value when you're writing production code. I don't know. Fuck it. You know, there's no real good reason to do that kind of shit. Comparing performance, loops versus iterators. You'll see here that the 4 version was, what would you say here? 4% faster. There you go. The 4 version was 4% faster. So you did all that work with the iterators, and you're 4% slower. But you have the fucking the bragging rights, you know. You did it for the, you know. You did it for the clout. That's why you do it.
Wait, no, it says iterator is slightly faster.
Yeah, wait.
That's not what I'm saying. I'm saying 19,234 for iterators, and I'm saying 19,620 for 4.
Yeah, nanoseconds per iteration.
Oh. Nanoseconds per iterator.
For cloud and speed.
It takes.
There you go. Oh, the iterator version was slightly faster. Okay, I read that wrong. Yes. Okay, there you go. So yes, you're right. Nanoseconds per iteration. I would prefer that come later, but sure. Okay, yes. So there you go. Well, now you have justification. Fuck, dude. Clearly, this is what God wanted. You're saving the whales one atom at a time. For a more comprehensive benchmark, yes, yeah, I like it. It's not even a comprehensive benchmark. Yeah, I'm not going to go into that. When you get to benchmark it, you'll be making a lot more money than where we're at. Okay, so buffer is a mutable array of type I32. Coefficients is a mutable array of type I64 of 12 elements. QLP shift is a type of signed integer of 16 bits. We say for I, and then we're saying 12 to the buffer length. Let prediction equals, and then we have this. So I'm saying this is where you go with it, right? Now, is this clearer than a 4? Cleaner than a 4? No, but this guy's got cloud, right? So fuck yeah. He's got .iter, .zip, .map, .sum. Good luck reading that shit. Job accomplished. Next. No, I mean, I actually don't think it's like, for me, that's actually pretty clean. That's the problem too. The problem is that the more you program, the cleaner that looks. And
I've done R before, so.
yeah. The less you program, the more fucked up that looks. Yeah. So program a lot, and it'll just start to make sense. Okay, so they want us to explain it. So I'll go ahead and explain it. Zip is going to take 2 elements from that, and it is going to pass them down to the next list as a tuple. So when you say zip, and I give it an iterator with 4 elements, zip will eat 2 of those elements, return a tuple of those 2 elements. Then it'll eat 2 more elements, return a tuple of those 2 elements, right? So that's how zip kind of works. So the first stop is the zip, and the second stop is the map, and the map is going to deconstruct those tuples, and it's going to say C times S. So the map is going to look at, so we're going to take 2 chunks of everything, and of those 2 chunks that we get, we're going to multiply the numbers together in those chunks, right? And because we're using multiplication, and you know, the left and the right side doesn't matter, we can just speak in terms of chunks, not lefts and rights. And then what we're going to do is, map is going to return 1 element. It gets a tuple of 2 elements. It returns 1 element, the product of that, right? So map is taking a tuple of 2 elements and returning the product, and then sum is going to add all of them together. So if we have a list of 8 items and we call this thing, we're effectively going to be multiplying 1 and 2, 3 and 4, 4 and 5. No, 1 and 2, 3 and 4, 5 and 6, 7 and 8. Those all get multiplied together. Then we're going to add the results of all of those in the sweep. And it's all lazy. So what does it mean when it says lazy? It means when I pull from that once, right? Well, it's not lazy. It's not lazy when you're summing. It's lazy before the sum. The sum has to visit all elements, so it's got to eat the whole thing. Does that make sense? Cool. And I have no idea what prediction is here. Linear prediction, mathematical operations to estimate future values based on linear functions of the previous samples. No fucking idea. I'm not a math guy. Brian?
I'm just confused. What is buffer being passed to C doing? You know, they're passing buffer at index. They're passing a slice of the buffer into C. From the previous 12 elements until the index.
What am I doing?
Inside SIP, you're passing a slice from the previous 12 up to the current index. And I don't understand what they're doing by passing that to SIP.
Oh.
I guess it's all right.
Are they even going to tell us what they're
It
doing?
says right there to calculate the value.
Just go to iterates through each of the 12 values and
Okay,
coefficients.
So it's sipping and putting them into buffer, I guess. Oh.
So buffer is to hold
Okay, so as you go, you store the previous values into buffer, and then what you're sipping with the current coefficient is the previous 12 values. That's what it's doing.
I think I'd have to look at zip. I don't know what zip is doing here.
So I think SIP is sipping the current value with the, whatever you pass to SIP.
I wanted to read the explanation.
Iterator and STD. Zip. Zips up 2 iterators into a single iterator of pairs. Okay. So I assumed when I described this wrongly that zip was taking 2 elements from one iterator and zipping them together. A zip takes 2 different iterators and it pulls 1 element from one element from the other. So here, the first element will be from coefficients. The second element will be from that buffer. That's what's happening. Right? So the buffer itself is a mutable array of I32s, and we're going to be creating a size of that buffer, which is the last 12 things. And we're going to take 1 from that and 1 from coefficient. You're going to have that become C and S. And then when you're done, you're going to write here's where it gets written. Okay. And then after you do that, you're going to write it right there. Buffer I equals prediction as I32 plus the delta. Okay. That is a really horrible example to show this shit, and I don't know what that does because I don't do linear algebra, but some kind of goofy shit. I don't
I
know.
feel like that's the most confusing way of doing this, whatever they're trying to do.
It's interesting with the last line of paragraph. It says
You know, I did one class one time. I had a lot of experience with Python. I used it for years and years and years and years and years. I like the language a lot. And I tried to teach a book called Think Python with Python. And I don't know if anyone's ever heard of Think Python. Anyway, The class was hilarious. Hilarious. I didn't want to teach it to begin with. I did this class called Automate the Boring Stuff with Python because we had a huge demand for that. And I thought that, I mean, to say that we had a huge demand for that, there was like 70, 65 people that showed up for that class. It was crazy. And we had 400 people apply. It was insane. Python is way bigger than Rust and all these other languages. Everyone wants to learn it even when they don't want to become a computer programmer. And everyone can stick through it until the end, and they all find out no one can get a job because no one wants an entry-level Python programmer. So it's a whole different ball field of problems associated with it. But I wanted to teach a Python book, and Think Python was open source. So you could download a copy of it, you know. And it was the most insanely difficult book to teach. It was just crazy. It was crazy. It was like the author must be the most geeky computer programming author ever. He is going through like fractals in the second class and all kinds of goofy shit. And I'm losing everyone on the math of it. And I'm like, look, don't worry about it. Just trust the guy on the math side of it. I mean, it's a fascinating book. Like 2 people in the class just were totally enamored. Obviously math geeks, you know, come straight from the math program. But I'm like, I don't fucking know how the Mandelbrot shit works, you know? Don't ask me. Look, we did it. It draws a pretty picture, and I can explain the Python, you know? I don't know. It just, there's definitely a point where you have to have, I think, some idea of what's going on there. And when you don't explain it, you know, you just start to chain things together. It's some math thing, you know? QLP shift. And I'm sure quantized linear, what is this? The QL has got to be quantized linear. What is the P? Here, let's look for it. QLP shift.
Prediction.
Let's see here if we can find what the load. No one knows what a QLP shift here is, huh?
QLP quantums, search for that.
So you also think quantized? Did I just bullshit you? Did I just sell that? QLP quantized. Quantized linear pre-coding. There we go. I was fucking right. I got 2 of the 3 right. I was like, what's the most confusing word with a Q? Quantized linear pre-coding, QLP. That could be what it stands for. I don't know, fucking know. Quantized linear module with quantized tensor as input. Yeah, math people really like quantized shit. Quantized linear pre-coding down here. So yeah, if you want to know what that shit is about, there you go. Read that thing. I don't know. I mean, I use modules that do this kind of stuff, but no one writes this, you know. No one has ever told me to write a quantized linear pre-coding algorithm. I'd say, where's the fucking, you know, RFC on that? They'd point to a math textbook and I would lose that job. All right. Yeah. Okay, and we're done. That's it.
Ryan was asking about how do you write a generic anonymous function?
I don't think you can write a generic anonymous function. I don't think that's even possible. You don't have a type argument for generics, and you don't have a place to declare it even.